Welcome back, inspectors, engineers, and future Level 2 and Level 3 professionals. Today, we are starting one of the most important chapters in non-destructive testing, visual testing, commonly known as VT. Now, many candidates underestimate visual testing because it appears simple. But let me tell you something from real field experience. Almost 80 to 90% of defects are first discovered through visual inspection before any advanced NDT method is even applied. Whether you are inspecting pressure vessels, piping systems, heat exchangers, structural steel, storage tanks, or refinery equipment, visual testing is always the first line of defense. In this chapter, we will cover inspection fundamentals, human vision, lighting theory, mirrors, borescopes, dimensional inspection, and the critical exam questions that repeatedly appear in ASNT, PCN, and ISO 9712 examinations. So stay focused, because many Level 3 candidates lose easy marks in VT simply because they ignore the fundamentals. Let's begin. Before we start, let's understand what you will achieve by completing this chapter. By the end of this training, you should be able to clearly define visual testing and understand exactly where it fits within an NDT program. You will learn the advantages and limitations of VT, and this is extremely important because examiners love asking questions about what visual testing can detect and what it cannot detect. We will study the anatomy of the human eye because understanding how inspectors see indications is fundamental to successful visual inspection. We'll discuss visible light, reflection theory, contrast generation, and why lighting angle can make a crack appear or completely disappear. You will also learn the difference between direct and remote visual testing. In the field, inspectors frequently use mirrors, borescopes, videoscopes, and CCD cameras, and you must know when each tool is appropriate. Finally, we'll cover dimensional inspection instruments and the critical examination questions that commonly appear in Level 2 and Level 3 certification exams. Keep one thing in mind throughout this chapter. Visual testing only detects surface and macroscopic indications. Remember this statement because it is one of the most frequently tested concepts in certification examinations. Here is our roadmap for this chapter. We'll begin by understanding the definition and industrial importance of visual testing. Then we'll explore the advantages and limitations. Next, we'll study human vision and eye anatomy, followed by lighting theory and reflection principles. After that, we'll discuss viewing angles, contrast enhancement, and inspection techniques. We'll move into inspection tools including mirrors, magnifiers, borescopes, and CCD cameras. Then we'll cover visual dimensional inspection equipment. Finally, we'll finish with examination-style review questions and a complete chapter summary. My recommendation is to watch this entire chapter without skipping sections, because many examination questions combine concepts from multiple topics. Now let's start with the foundation of visual testing. Visual testing is the oldest inspection method known to industry. Long before ultrasonic testing, radiography, magnetic particle testing, or phased array existed, inspectors relied on their eyes to evaluate components. Even today, every major refinery, power plant, fabrication shop, and offshore facility begins inspection activities with visual testing. Why? Because VT is fast, inexpensive, and highly effective when performed correctly. In practical terms, VT allows us to identify visible defects, fabrication errors, damage, corrosion, and dimensional problems before investing time and resources in more advanced inspection methods. Think about a refinery turnaround. Thousands of welds may need inspection. The first assessment is almost always visual testing. Only after VT acceptance are additional NDT methods performed. That is why visual testing remains the foundation of every quality control program. Let's define visual testing exactly as examiners expect. Visual testing is the observation of a test object, either directly using the human eye or indirectly using optical instruments, for the purpose of evaluating surface discontinuities and quality nonconformities. Notice two critical words here: surface and macroscopic. These two words are extremely important. Visual testing is designed to detect discontinuities that are visible on the surface. Examples include cracks, corrosion, oxidation, pitting, scratches, gouges, and weld discontinuities. VT is also used to identify quality issues such as misalignment, dimensional deviations, incorrect fit-up, and physical damage. Now here's the exam trap. Can VT detect subsurface cracks? The answer is no. Can VT detect internal porosity? Again, no. For those types of discontinuities, we require methods such as ultrasonic testing or radiographic testing. Whenever you see a question asking about the limitation of VT, remember, surface only, macroscopic only, no subsurface detection. Let's discuss why visual testing is so widely used throughout industry. First, visual testing is inexpensive. Compared to radiography or ultrasonic testing, the equipment cost is extremely low. Second, very little equipment is required. In many cases, proper lighting and a trained inspector are sufficient. Third, results are immediate. You do not need film processing, data analysis software, or extensive post-processing. You can evaluate the condition of a component instantly. Fourth, visual testing is highly portable. It can be performed virtually anywhere. However, every inspection method has limitations. Visual testing can only detect surface discontinuities. It cannot see beneath the surface. Another limitation is that VT requires a direct line of sight and adequate lighting. Poor lighting can completely hide critical indications. Interpretation is also subjective. Two inspectors may interpret the same indication differently depending on their experience. Finally, inspector fatigue can significantly reduce inspection effectiveness. This is why proper training, lighting, and inspection procedures are essential for reliable visual testing. Now we move into a topic many candidates ignore: the science of human vision. As inspectors, our eyes are actually inspection instruments. Understanding how vision works helps us understand why some indications are easily detected while others are missed. The process begins when light reflects from a test object and enters the eye. The cornea and lens focus this reflected light onto the retina. The retina contains specialized receptors called rods and cones. These receptors convert light into electrical signals. Those signals travel through the optic nerve to the brain. The brain then interprets the image and creates what we call visual perception. Notice something important. The brain never sees the object directly. It sees reflected light information. This is why lighting conditions are so important in visual testing. No reflected light means no useful visual information. Remember this concept because it forms the foundation of all visual inspection techniques. Let's examine the major components of the eye. The cornea is the transparent front surface and provides most of the eye's focusing power. The pupil is the opening through which light enters the eye. The iris controls the size of the pupil and therefore regulates the amount of incoming light. Think of the iris as the automatic light control system. Behind the iris is the lens. Unlike the cornea, the lens can change shape. This allows the eye to focus on objects located at different distances. Here is an important exam question. Which structure provides fixed focusing power? The answer is the cornea. Which structure provides variable focusing power? The answer is the lens. Many candidates confuse these two functions, so remember this distinction carefully. In this section, we'll examine the primary external and functional components of the human eye and understand how they contribute to vision. Let's begin with the cornea. The cornea is the transparent, highly curved front surface of the eye. Its main function is to allow light to enter while providing most of the eye's focusing power. Because of its curved shape, the cornea bends incoming light toward the retina. Next is the pupil. The pupil is the circular opening at the center of the iris. It appears black because light entering through it is absorbed inside the eye. The pupil regulates the amount of light that reaches internal eye structures. Surrounding the pupil is the iris. The iris is the colored muscular structure of the eye. It controls pupil size by contracting and relaxing in response to light intensity. In bright conditions, the pupil becomes smaller to reduce light entry. In dim conditions, it expands to allow more light in. Now let's focus on the lens. The lens is a flexible, transparent structure located behind the iris. Its function is to fine-tune focus by changing shape, allowing us to clearly see objects at different distances. This process is called accommodation. When viewing nearby objects, the lens becomes more curved or rounded to increase focusing power. For distant objects, it becomes flatter. Understanding these structures helps explain how the eye controls light entry and maintains sharp focus. Let's begin with the retina. The retina is a light-sensitive layer located at the back of the eye. Its primary function is to convert incoming light into electrical impulses, which are then transmitted to the brain for visual interpretation. This conversion is performed by specialized photoreceptor cells called rods and cones. Next are the rods. Rods are highly sensitive to low light and are responsible for black and white vision, especially in dim environments. They play a critical role in peripheral vision and motion detection, helping us see in darkness. Now let's look at the cones. Cones function best in bright light and are responsible for color vision and fine detail recognition. They are densely concentrated in the central region of the retina, enabling sharp and accurate visual perception. At the center of the retina lies the macula. This small but highly important area is responsible for central vision and provides the sharpest image details. Activities such as reading, driving, and inspecting welds depend heavily on macular function. Moving to the optic nerve. The optic nerve acts as the communication pathway between the eye and the brain. It carries the electrical signals generated by the retina, allowing the brain to process visual information. Surrounding the eyeball is the sclera. The sclera is the tough white outer protective layer of the eye. It maintains the eye's shape and provides attachment points for several eye muscles. Finally, the ciliary muscle. This muscle controls the shape of the lens to adjust focus. When viewing nearby objects, the lens becomes rounder. When focusing on distant objects, the lens flattens, allowing clear vision at varying distances. Understanding these components helps explain how the human eye captures, processes, and interprets visual information. Now we enter one of the most critical VT topics: lighting. Without light, visual testing simply does not exist. Remember this principle. We do not inspect the object directly. We inspect reflected light coming from the object. Visual testing generally operates within the visible spectrum of approximately 360 to 830 nanometers. That range is frequently tested in certification exams, so memorize it. Now let's discuss the 4 types of light used in VT. First, incandescent light, produced by filament lamps and carbon arc sources. These provide broad-spectrum warm illumination. Second, luminescent light. Examples include LEDs, lasers, and fluorescent lamps. These are highly efficient and widely used in modern inspection. Third, polarized light, used to reduce glare and analyze surface characteristics through interference patterns. Fourth, coherent light, typically laser light. This has uniform wavelength and phase and is used for highly precise measurements. From an inspection perspective, the purpose of lighting is simple. Create sufficient contrast so defects become visible. No contrast means no reliable detection. Remember that. Light reflection is the foundation of defect visibility. Surface condition determines how light behaves. On a smooth surface, light produces specular reflection. Specular reflection behaves like a mirror. The angle of incidence equals the angle of reflection. For example, if light strikes at 45 degrees, it reflects at 45 degrees. This creates strong directional reflection. Now consider a rough surface. Rough surfaces create diffuse reflection. Instead of reflecting in one direction, light scatters in multiple directions. Why is this important? Because defects such as cracks, pits, corrosion, and scratches disturb the surface profile. That disturbance changes reflection patterns. Your eye notices this difference as contrast. In simple field language, cracks become visible because they reflect light differently from sound metal. This contrast is the basis of visual testing. One of the most powerful techniques in VT is controlling light angle. Small defects often disappear under direct lighting, but the same defect becomes obvious when illuminated from the side. This is called oblique lighting. Oblique lighting creates tiny shadows inside cracks and pits. Those shadows enhance contrast and reveal depth. This is especially useful for shallow surface cracks. Local lighting improves illuminance and increases visibility of indications. Experienced inspectors often use a movable flashlight. Why? Because moving the light source changes the shadows. If the indication appears and disappears consistently, it is likely a real discontinuity. If not, it may be dirt, stain, or surface artifact. This technique is heavily used during weld inspections. Exam question: best lighting method for shallow cracks? Answer: oblique or angled lighting. Now we discuss critical viewing parameters. These numbers are extremely important for exams. Maximum viewing distance: 24 inches or 600 millimeters. The eye must remain within this distance from the inspection surface. Minimum viewing angle: 30 degrees to the inspection surface. Anything less reduces inspection quality. Recommended viewing angle: between 60 and 90 degrees. This gives the best visibility and least distortion. Another important rule: deviation from normal viewing axis should not exceed 45 degrees. Beyond that, apparent size and location become distorted. Peripheral vision also plays a role. Peripheral vision helps detect high-contrast indications across large areas. However, fine inspection should always rely on direct focus. Memorize these numeric thresholds carefully. There are 2 primary VT techniques: direct visual testing and indirect, also called remote visual testing. Direct VT means the inspector is physically present and has immediate visual access to the surface. Even if you use magnifiers or mirrors, it is still direct VT, as long as you are physically near the component. Examples include weld inspection, fit-up checks, and flange alignment verification. Indirect or remote VT is used when direct access is impossible. This involves borescopes, remote cameras, and optical systems. Typical applications include internal piping, heat exchangers, turbine blades, aircraft engines, deep cavities. Remember this exam statement. Remote VT and indirect VT mean the same thing. Now we begin VT equipment. An inspector's effectiveness depends heavily on selecting the right inspection tool. In this section, we cover mirrors, magnifiers, optical scopes, borescopes, and CCD imaging systems. Every Level II or Level III inspector should understand not only what these tools are, but when to use them in real field conditions. The most common VT tool in NDT is the dental mirror. This is a favorite exam question. Dental mirrors allow inspectors to observe areas not directly visible. Examples include weld root regions, backside surfaces, and inaccessible corners. Next is the movable end mirror. This uses a pivot mechanism so inspectors can change viewing angle. Very useful inside bores, castings, and threaded holes. Then we have telescopic handle mirrors. These extend reach into remote locations. But remember, mirrors alone are not enough. Proper lighting remains essential. A mirror without light is useless. Field inspectors commonly combine mirrors with high-intensity flashlights. Magnifiers improve inspection accuracy by enlarging suspicious areas. There are 3 major handheld magnifiers. Highest quality, Hastings triplet. This corrects both spherical and chromatic aberration. That makes it the best handheld magnifier. Second, Coddington magnifier. Its groove design removes marginal light rays and improves image clarity. Third, double plano convex magnifier, simpler and less expensive, provides partial correction only. Exam ranking question appears often. Remember, Hastings triplet greater than Coddington greater than double plano convex. Pocket microscopes provide higher magnification than standard magnifiers. Typical magnification ranges from 25 times to 60 times. These are compact and portable. Now let's discuss eye attachments. 2 major types exist. First, visor type mounted on the head using a band. Hands remain free. Typical magnification ranges from 1.5 times to 15 times. Second, loop held like a monocle or attached to glasses. Magnification ranges from 2 times to 18 times. Important exam distinction. Loop has wider magnification range than visor. Borescopes are essential for remote visual inspection. They inspect internal surfaces inaccessible to direct viewing. Examples include pipes, tubes, turbine passages, and engine bores. 2 main types exist. First, rigid borescope. These provide excellent image quality, but only work in straight paths. They cannot navigate bends. Typical use: heat exchanger tubes and straight bores. Second, fiber borescope. Flexible and capable of navigating curves and bends. This makes them ideal for complex geometries. Exam question: rigid or fiber, which handles bends? Answer: fiber borescope. The modern remote VT increasingly uses electronic imaging. This is where CCDs come in. CCD stands for Charge-Coupled Device. These are miniature electronic cameras. Instead of fiber bundles transmitting images optically, CCD sensors convert images into digital signals. Advantages include real-time display, digital zoom, image storage, remote review, image enhancement. In modern oil and gas inspections, crawler systems carrying CCD cameras inspect long pipelines without shutdown. This dramatically improves efficiency. Exam point. CCD can replace fiber optic imaging systems. Visual testing is not only defect detection, it also includes dimensional inspection. Dimensions verify whether a component meets engineering tolerances. This includes length, thickness, height, diameter, alignment, flatness in QA/QC. Dimensional nonconformance can cause failure even when no defect exists. That is why dimensional inspection is essential. Linear measurement tools measure distance between 2 points. Examples include rulers and tape measures. Simple but widely used. Calipers are more precise. They measure internal diameter, external diameter, and depth. Mechanical gauges use threaded spindles for accurate dimensional checks. Surface plates provide highly flat reference surfaces. Height gauges work with surface plates to measure variation from that reference. Dial indicators detect very small deviations using needle movement. Exam tip. Surface plate provides flat reference. Height gauge measures variation from that reference. Two-axis instruments measure geometry along X and Y axes. These are important for flatness, alignment, and profile evaluation. First, optical flat. Used to inspect extremely flat surfaces, interference bands reveal deviations. Second, optical comparator. Also called an optical projector. It projects an enlarged shadow of the test object onto a screen. This allows accurate dimensional comparison. Third, autocollimator. Used for alignment, perpendicularity, and flatness of large surfaces. Very common exam trap. Which instrument projects an enlarged shadow? Answer, optical comparator. Let's test your understanding. Question 1. What discontinuities does VT detect? Correct answer, surface macroscopic discontinuities. Question 2. Which eye component converts light into electrical signals? Correct answer, retina. Question 3. Most common VT tool? Correct answer, dental mirror. Question 4. Which instrument projects enlarged shadow? Correct answer, optical comparator. If you missed any of these, review earlier slides. Second knowledge check. Question 1. Which parts focus light onto the retina? Correct answer, cornea and lens. Question 2. What is crucial for successful VT? Correct answer, contrast detection. Question 3. 4 types of VT light? Correct answer, incandescent, luminescent, polarized, coherent. Question 4. Good viewing angle? Correct answer, 60 to 90 degrees. These are classic certification questions. Let's summarize the entire chapter. Visual testing evaluates macroscopic surface discontinuities. VT requires 3 basics: eyes or optics, adequate lighting. Knowledge of acceptance criteria. VT is fast, portable, and inexpensive. Its major limitation, surface only. We studied human vision, light theory, reflection, viewing geometry, direct and remote VT, inspection tools, and dimensional instruments. Master these fundamentals. They are heavily tested in Level II and Level III certification. Now memorize the critical numbers. Visible spectrum, 360 to 830 nanometers. Maximum viewing distance, 24 inches or 600 millimeters. Minimum viewing angle, 30 degrees. Good viewing angle, 60 to 90 degrees. Pocket microscope, 25 times to 60 times. Fiber bore scope, max length, 300 feet. These numbers frequently appear in exams. Flashcard them. Use this checklist before your examination. Can you define VT? Can you explain light theory? Can you distinguish specular and diffuse reflection? Can you identify all VT tools? Can you explain dimensional inspection instruments? If any box remains unchecked, revisit that topic. Certification success comes from repetition and mastery. Congratulations! You have completed Chapter 18, Visual Testing. Do not underestimate VT. In real industry, visual testing prevents failures before expensive NDT methods are applied. A strong VT foundation makes you a better inspector, better engineer, and stronger Level 3 professional. Review the quiz questions again. Memorize the critical numbers. And most importantly, train your eye to observe what others miss. See you in the next chapter.